Welcome to Discover Daily with Perplexity. It's a series where I come across random topics and I start exploring them with perplexity on a daily basis. The idea is that you don't wait for becoming perfect at something and then sharing with somebody. Instead, you share the journey and start getting better at it together. Today, we'll be trying to figure out what is the difference between fission and fusion energy and what is the stage at which we are, what are the challenges related to them. It's going to be a much more basic explanation and will be followed up with my attempts at getting a better understanding of them later. What is the difference between fission and fusion?
Fission involves splitting a heavy nucleus into lighter nuclei, releasing energy and radioactive byproducts. Fusion combines light nuclei to form a heavier nucleus, releasing more energy without long-lived radioactive waste. Fusion powers stars, while fission is used in nuclear reactors.
It is called nuclear reactions because it involves only the nuclei and not the electrons. Is that correct?
Yes, that's correct. Nuclear reactions, such as fission and fusion, involve changes in an atom's nucleus and do not directly involve the electrons surrounding the nucleus. These reactions result in the transformation of elements and the release or absorption of energy. Here's a bit more detail on each. Nuclear fission. Process. In nuclear fission, a heavy atomic nucleus, such as uranium-235 or plutonium-239, splits into two or more lighter nuclei, along with a few neutrons and a large amount of energy. Applications. Fission is used in nuclear power plants to generate electricity and in nuclear weapons. Byproducts. It produces radioactive waste, which requires careful handling and disposal. Nuclear fusion. Process. In nuclear fusion, two light atomic nuclei, such as isotopes of hydrogen like deuterium and tritium, combine to form a heavier nucleus, releasing energy in the process. Applications. Fusion is the process that powers stars, including our sun. It has the potential for use in fusion reactors for clean energy production, though it is still largely experimental for practical energy generation on Earth. Byproducts. Fusion produces minimal radioactive waste compared to fission and is considered a cleaner energy source. Both processes release energy due to the conversion of mass into energy, as described by Einstein's equation EMP2.
So, if we want to produce energy on Earth, what is our better choice? Is it fusion reactors or fission reactors?
Currently, fission reactors are the better choice for producing energy on Earth due to their established technology and proven track record. Fusion reactors offer potential advantages like abundant fuel and minimal waste, but they remain experimental and not yet viable for large-scale energy production.
Can we say that fission reactors are used on Earth to generate energy, but whereas can we consider that Sun as a fusion star?
Yes, nuclear fission reactors are used on Earth to generate energy by splitting heavy atomic nuclei. The Sun, on the other hand, is a fusion star, producing energy by fusing light atomic nuclei.
What are the constituents of a nucleus?
The constituents of a nucleus are protons and neutrons, collectively known as nucleons. Protons carry a positive charge, while neutrons are neutral. These nucleons are bound together by the strong nuclear force.
Doesn't electrons appear anywhere in the nuclear or nuclear fusion or fission?
Electrons are not directly involved in nuclear fission or fusion reactions, as these processes primarily involve changes in the nucleus. However, electrons can participate indirectly, such as in electron capture, where an electron is absorbed by the nucleus.
In fission, What are the challenges that we currently foresee in making sure that that becomes the major source of energy on earth?
The main challenges in making fusion a major energy source include achieving net energy gain, developing materials that withstand extreme conditions, managing tritium supply, and addressing engineering and regulatory hurdles.
So can we consider that fusion is challenging in the short term and we should concentrate on fission reactors?
Yes, fusion is challenging in the short term due to technical and material hurdles, making fission reactors a more immediate focus for energy production.
Then why is fission reactors not so popular?
Fission reactors are not as popular due to concerns about radioactive waste, the risk of catastrophic accidents, high costs, and public opposition. These factors have limited their expansion despite their ability to produce low-carbon energy.
Based on the proofs that are available, do you think the risks of radioactive leakages in fission reactors are valid, or do you think it's exacerbated due to the political opportunism?
The risks of radioactive leakages in fission reactors are valid due to potential accidents and waste management challenges. However, political factors can amplify public concern and opposition, affecting the perception and adoption of nuclear energy.
Does it mean that solar energy is the most risk free and the one that we should place all our bets on?
Solar energy is a low-risk renewable source with environmental benefits, but it requires significant land and materials, and its efficiency depends on sunlight availability. Diversifying energy sources, including solar, is advisable rather than relying solely on one.
Has anybody tried creating fission reactors on satellites or moon or close by planets and then calculate if it does make sense to move the storage of that energy to Earth, or maybe there's some way to transport that energy back to Earth?
No fission reactors have been built on satellites, the moon, or nearby planets for energy production and transport back to Earth. Current efforts focus on using nuclear reactors for power on the moon to support lunar exploration and habitats.
Is the experiment of generating fission energy on moon a successful one?
The experiment of generating fission energy on the moon has not yet been conducted. NASA is still in the planning and development stages for a lunar fission reactor, with a demonstration expected in the early 2030s.
Looks like for the time being, we should put a decent amount of our resources on capturing the solar energy. Just to get a sense of it, what is the ratio of energy that is required by humans on planet Earth compared to the total energy that reaches Earth from sun?
The Earth receives about 173,000 terawatts of solar energy from the Sun, which is over 10,000 times the current global energy consumption. This indicates a vast potential for solar energy to meet human energy needs.
What are the current challenges in capturing solar energy so that 100% of the human energy needs are sourced from solar energy capture? What are the current challenges in capturing solar energy so that 100% of the energy requirements of human are from solar?
Current challenges in capturing solar energy include inefficiencies in photovoltaic technology, high initial costs, land use competition, intermittency issues, and storage limitations. These factors hinder the ability to fully meet global energy demands with solar power.
How about making distributed solar energy consumption as well as storage?
Distributed solar energy generation, which involves small-scale, decentralized solar systems, offers benefits like reduced grid strain and environmental impact. However, challenges include intermittency, storage needs, and grid integration. These factors affect its potential to fully meet global energy demands.
For somebody who owns a farm, what is the most cost effective way in which they can capture solar energy and attain energy self sustenance?
For a farm owner, the most cost-effective way to capture solar energy is by installing distributed solar photovoltaic systems. These systems offer local clean energy generation, reduced grid dependency, and potential savings through government incentives and net metering.
Considering the seasonality or the uneven distribution of solar power source, is it possible to convert the additional energy into Bitcoin and then later use that Bitcoin to buy the power from the grid?
Yes, it's possible to convert excess solar energy into Bitcoin through mining during periods of surplus and later use the Bitcoin to purchase grid power. This approach can help manage the intermittent nature of solar energy.
Considering that we generally need energy, compute, intelligence, and resources for solving any big problem, do you think that considering energy and the cost of energy and the cost of compute would go to zero in short term, and also considering that because of AI the cost of compute and intelligence also will go to zero?
In the short term, energy and compute costs are unlikely to go to zero. AI can optimize resource use, but its growing computational demands and associated costs present challenges. Energy prices also depend on infrastructure and resource availability.
Considering that
Considering that energy and compute costs are unlikely to go to zero in the short term, it is essential to focus on optimizing resource use and improving efficiency. Here are some strategies. 1. Energy efficiency. Implement energy-efficient technologies and practices to reduce consumption and costs. 2. Renewable energy. Invest in renewable energy sources like solar, wind, and hydro to reduce reliance on fossil fuels and stabilize costs. 3. AI optimization. Use AI to optimize processes, improve efficiency, and reduce waste in various industries. 4. Grid management. Enhance grid management systems to better integrate renewable energy sources and balance supply and demand. 5. Energy storage.
Thank you.